Hi there, and welcome back to the channel. Throughout this series of videos, you will be introduced to topics in optimal control and estimation in a way that you can draw almost complete idea about optimal control and optimal observers. Most of the introduced materials during this journey is borrowed from the book, Applied Optimal Control, Optimization, Estimation, and Control, which is written by Arthur Bryson. This is the third part of this series. But before jumping into the subject of this video, let me briefly go through the topic introduced by Part 2 of the series. In Part 2, we have covered parameterized optimization with equality constraints where necessary conditions for finding stationary points are covered. Please find the link for this topic in the description. We have a scalar index of performance L of x and u that we want to minimize. This function is subjected to the constraint f of x and u equal to 0. Here, f of x and u is n equations where n is the dimension of the variable x. We have shown that the necessary conditions of having stationary points for the undertaken problem above are as following. F of x and u have to equal 0 along with the partial derivative of the Lagrange function h with respect to both variables x as well as u. In solving for these necessary conditions, we have to solve for two n plus m equations. Now let me introduce the topic of this video. Here, we want to drive a sufficient condition for the stationary point that we have found to be a minimum point. To accomplish that, let me remind you that we have an index function L of x and u as well as an equality constraint f of x and u. These two functions are combined together through the h functions as shown. Through which and with a simple manipulation, we can write the index function in terms of the h function and the f function as shown. Before jumping right into the derivation of the sufficient condition, let me introduce some concepts about the increment of functions along with first and second derivatives. Any function f of x is said to have a local optimum at point x star if there exists a positive and constant parameter, say, epsilon, where all points x in some domain D that satisfies the relation absolute of the difference between any point x in D and the optimum point x start is less than the positive parameter epsilon. Then the increment of the function delta f will have the same sign. To illustrate this concept, consider the function f of x shown by the figure below. This function has two stationary points as shown by x max and x min. At these points, the slopes of the tangent lines are 0. Slope of a tangent line is the first derivative of the function f of x. Now, consider some points around these two stationary points as indicated by the orange-colored points. As long as these points are inside the circle whose radius is the constant epsilon, then we can say that these points belong to the domain that is produced by the circle. If you notice closely, you can see that at these points, the increment of the function delta f will have the same sign always. Keep in mind that the increment of a function refers to the change in the function's value resulting from a change in its input variable. It is calculated by subtracting the function's initial value at a certain point from its final value at another point, while considering the change in the input variable. This concept is showing how to find stationary points of a given function, but it does not specify whether these points are maximum or minimum. For that, we need to find the second derivative of the function at these points. As we know that the first derivative describes the rate of change of a function, while the second derivative in turn shows how the slope or rate of change of the function's slope is changing. The second derivative provides information about the concavity or curvature of the graph of a function as follows. Positive second derivative indicates a function that is concave up or increasing at an increasing rate. Thus, if the slope or rate of change of the function's slope is positive, then we can say that we have a minimum point as shown by the green box. On the other hand, a negative second derivative suggests that the function is concave down or decreasing at an increasing rate. Thus, we have a maximum points as shown by the green box. Finally, a 0-second derivative implies a potential point of inflection where the concavity changes. This is also shown by the green box on a point in between the 2 points x max and x min. Now, let us apply these concepts on our original optimization problem. To second order, the differential changes of L and F away from a normal point x and u are given as followings. For L and for F. Now, let us assume that the normal point x and u satisfies the given constraint f of x and u which equals to 0. Here, we want to examine the behavior of the index function L in an infinitesimal neighborhood of the normal point while keeping f of x and u equal to 0 to its second order. From the previous concepts, we have f of x and u is 0 along with its differential df. Thus, from the df shown function, we can have an explicit expression for the differential dx as. Keep in mind, if our nominal point is a stationary point, then from the necessary conditions we can have the partial derivative of the Lagrange function h with respect to both variables x as well as u along with df equal to 0. By substituting these three facts into the function of dl, we can have the following new expression for dl. We also can substitute the obtained expression for dx, which gives the following. Now, by differentiating both sides to u one more time and then simplify the terms through vector and matrix multiplications, we can have the final expression for the sufficient condition for minimum as shown. Thus, if the second derivative with respect to the decision variable vector u is positive, then we can say that our found stationary point is a minimum point. To sum up the concepts we have driven so far in this part and the previous part, we can say the following. We have an optimization problem where we want to minimize the function L of x and u, and at the same time we need to satisfy the equality constraint f of x and u as well. Remember that we can combine these two functions into a single function h of x and u. Now to find the stationary points, we need to solve the following set of equations. These equations are the necessary conditions for having stationary points. Then, to specify whether these stationary points are minimum or not, we have to check the definiteness of the second derivative of the function L with respect to the decision variable u. This check is our sufficient condition. Let me now introduce an example. Consider a function L of x and u as shown where it is desired to find the value of the scalar variable u that minimizes the function L. At same time, this value of the variable u has to satisfy the constraint given by the function f of x and u as shown. All involved variables x, u, and constants a, b, and c are scalars. The curves of constant L are ellipses, with L increasing with the size of the ellipse, whereas the function of x and u is a hyperbola with two branches. This is illustrated by the figure. Clearly, the minimum of L satisfying the constraints is when the ellipse is just tangent to the hyperbola. To express this analytically, first build the h function from both L and f functions as shown. Second, apply the necessary conditions to compute the stationary points. This is shown as following. Solving these three equations simultaneously results in the following solution. Now let us check if our solution is minimum or not. To do that, we simply apply the sufficient condition. This step gives the shown result, which is clearly a positive number. Thus our computed stationary are minimum points. We can also compute the corresponding minimum value of the function L by simply plug in the values of our minimum points in the function L. This minimum value of the function L is given as. One last point that should be stated here is that we have two minimum points which are shown by the red little circles on the figure. I hope the materials presented in this video are helpful in understanding the introduction to the optimal control theory. Thank you for watching the video and please like the video and subscribe to the channel. See you soon. Hopefully.